Hello, this is section 2.6, second derivative and concavity. Since the derivative of a function is also a function, we can take the derivative of the derivative. Theoretically, you can do this indefinitely. The derivative of the derivative is called the second derivative, and the notation is f double prime of x, d squared y over dx squared, or capital D squared sub x of f of x. And the derivative of the second derivative is called the third derivative, with the notation below. And the derivative of the third derivative is called the fourth derivative, with the notation below. Notice how the prime notation, because you'd be doing lots of primes, is we make it look like an exponent, but the parentheses around the exponent are what indicate it's a derivative and not an exponent. And so on. Just like how the first derivative measures the slope of the tangent line at a point, the second derivative measures the concavity of a function at a point. That is, how is the function curved at that point? It can either be concave up, shaped like a cup, so it'll be curved like this, or concave down, shaped like a frown, so it'll be curved like this. Now, it doesn't have to be as extreme as what I just drawn, but it will have some upward curvature or some downward curvature. Example 1, find the second derivative of the following functions. So, as indicated in the definition, before you can find the second derivative, you do need to find the first derivative. So, y prime would equal 4x cubed minus 6x. Now, I need to bring that negative 2 down, so it's going to become minus 2x to the negative 3. And then y double prime would equal 12x squared minus 6. Now, when I bring the negative 3 down, a negative times a negative would become plus 6x to the negative 4th. Part B. So the first derivative, f prime of x, would equal 9x squared minus 8x. And then the second derivative would equal 18x minus 8. And then part C, before I take the derivative, I am going to rewrite it as 2x minus 1 to the 1/2, so that I can see that it's going to be a chain rule, with the outside equal to the 1/2 power, and the inside is equal to 2x minus 1. So now the first derivative will equal 1/2 to the negative 1/2 times 2, and then the 2x minus 1 goes inside. Before I take the second derivative, I am going to simplify the 1/2 times 2, so that the first derivative is just 2x minus 1 to the negative 1/2 power. And then y double prime would equal negative 1/2 to the negative 3/2 times 2, with the 2x minus 1 on the inside. And again, the 1/2 and 2 will cancel out, but notice the negative does not. So we get negative 2x minus 1 to the negative 3/2 for the derivative. Example 2, find the first four derivatives of f of x. So the first derivative would equal 12x squared plus 10x. The second derivative would equal 24x plus 10. The third derivative would equal 24. And the fourth derivative would equal 0. And actually, this I'm hoping gives you an idea for polynomials what the nth derivative would be. So if you have a 7th degree polynomial, the 8th derivative will always be 0. So if you take the derivative that's 1 more than the degree, you will get to 0 every single time for a polynomial. Example 3. Let f of x equal this. Part A, how fast is f of x changing at 1 comma 10? So changing indicates a rate of change or slope. So in order to answer this question, I'm going to find the derivative. And now to answer the question, I need to plug 1 into the derivative, which would equal 12 plus 18 minus 6, which is 24. So f of x is changing at a rate of 24 at 1 comma 10. Now, how fast is the first derivative changing? Well, just like how the first derivative tells us the rate of change for the original function, second derivative tells us the concavity of the original function, but it tells us the rate of change for the first derivative. So I'm going to find the second derivative now. We get 36x squared plus 36x minus 6. And then f prime of 1 is 36 plus 36 minus 6, which is 66. So f prime of x is changing at a rate of 66 at 110. Now, is f of prime of x increasing or decreasing at 110? Well, since f double prime of x is greater than 0, f single prime of x is increasing. So a couple definitions. Critical point. The critical point of a function f of x are, that should say points, the values of x such that f prime of x is equal to 0, or f prime of x is undefined. So in other words, if you have a horizontal tangent line or an undefined tangent line, we are going to be calling these critical points. Inflection points. The inflection points of a function f of x occur where the concavity changes. This can only occur at values of x such that f double prime of x equals 0, or f double prime of x is undefined. The key thing I want to point out here is we aren't guaranteed that every 0 and undefined point of the second derivative is an inflection point, but the only places inflection points can occur are at these two places. So example 4, consider the function f of x equals 9x plus 6x to negative 1. Find the critical points, intervals on which f of is increasing, and intervals on which f is decreasing. So first, to find the critical points, that's to find the derivative first, which is 9 minus 6x to the negative 2. And then I need to figure out when does that equal 0. Subtract 9, subtract 9, negative 6x negative 2 equals negative 9, divide by negative 6, divide by negative 6, x to the negative 2 equals 3 halves, raise it to the negative 1/2 power, raise it to the negative 1/2 power, and we get x, well, technically the absolute value of x is equal to the square root of 2 over the square root of 3. So why did it become 2 over 3? Well, we have a negative exponent, so we have to flip it, and then the 1/2 power is the square root. I am going to rationalize this by multiplying by the square root of 3 over square root of 3. We get the absolute value of x is the square root of 6 over 3. Be careful, you cannot reduce the 6 over 3 because one's in the square root and one is outside of the square root. And finally, to get rid of the absolute values, we're going to get a plus or minus square root. Now you might think these are our only critical points, but I wanted to point out that f prime of x can also be written as 9 minus 6 over x squared. So because there's a fraction here, we have to think of where it's undefined. F prime of x is undefined when x equals 0. Because if we plug 0 into the denominator, we get dividing by 0, which is not allowed. So our critical points are negative square root of 6 over 3, comma, 0, and then positive square root of 6. So we got 3 critical points for this function. Now you need to find the intervals on which f is increasing and the intervals on which f is decreasing. And we are going to use the fact that the first derivative will tell us this if it's positive or negative. And the only time it can switch are at the critical points. So that means if I do a number line with the critical points on it, and we're equal to 0 right here, 0 right here, undefined right here, that we just need to pick 4 test points. And we want to, because I'm worried about whether it's increasing or decreasing, not whether it's positive or negative, we have to plug these into the first derivative. So actually, I am going to just bring that first derivative down again onto this page. We got 9 minus 6x to the negative 2. And the square root of 6 divided by 3 is approximately 0.8. So then I probably would pick negative 1, negative 1/2, positive 1/2, and positive 1 as my test points to see if the first derivative is positive or negative. So f prime of negative 1 is 9 minus 6 times negative 1 to the negative 2. Be careful, I get too many students that do the 9 minus 6 first and get 3. Remember, you have to do multiplication before you can do subtraction. And even before multiplication, you have to do exponent. And we get 3. So I'm just going to put a big plus sign there for positive. And then f prime of negative 1/2, which would be 9 minus 6 times negative 1/2 to the negative 2. That comes out to be negative 15. Again, a big minus sign there to mean negative. and then f prime of positive 1/2, which is 9 minus 6, the 1/2 to the negative 2. Let's see what that comes out to be. That's also negative 15. So we got a negative there. I guess I should have wrote a little smaller. But f prime of 1, which is 9 minus 6 to the 1 to the negative 2, which is 3, which is positive. So then that means it's increasing here and here. Well, those two intervals are represented by negative infinity, negative square root of 6 over 3, union square root of 6 over 3 to infinity. And then it's decreasing on these two intervals. But be careful. A lot of people want to combine this into one, but remember, technically undefined right here, which keeps this split into two separate intervals. So then it's decreasing from negative square root of 6 over 3 to 0, union 0 square root of 6 over 3. And we have answered the. Then the last example for the notes. Consider the function g of t. Find the inflection points, intervals on which g is concave up, and intervals on which g is concave down. So I'm going to need the second derivative for this. So g prime of t would be 60t to the fourth plus 60t cubed minus 240. And g double prime of t would be 240 t cubed plus 180 t squared, and then actually 0. So did I do that right? Yep. So now I need to find where my inflection points may be. But remember, we're not going to know for sure if they're inflection points until we do the number line. With critical points, you know what they are right away. With inflection points, you have to wait until after the number line. This is our second derivative is still a polynomial. So there's no undefined points. So our inflection points can only be when our second derivative is equal to 0. Well, we get t squared can be factored out. And then we get t squared equals 0, which implies t equals 0. Or 240t plus 180 equals 0, which implies t is, well, subtract the 180 from both sides and divide by 240, but that can be reduced to negative 3/4. So those are the only two spots where we can have inflection points, but they aren't guaranteed to be inflection points. So now go to my number line, plot those, so we get negative 3/4, 0. My test points, negative 1, negative 1/2, and positive 1. So then g double prime of negative 1, which is 240 to the negative 1 cubed plus 180 times negative 1 squared, which is negative 60. So I got a negative sign there, and then g double prime of negative 1/2 equals 240 times negative 1/2 cubed plus 180 times negative 1/2 squared. and we get 15 there. So it's positive. And then G double prime all of 1, which is 240 cubed plus 180 1 squared, which actually, what does that come out? 420. So that's also positive. So then our inflection points I forgot, but it's 0 here and 0 there, are only at x equals negative 3/4, because it went from negative on one side to positive on the other. But at 0, because it went from positive to positive, it did not change. We don't consider 0 an inflection point. So we only have one inflection point here. And then it's concave. I'm going to do concave down first. Because concave down is where the second derivative is negative, which is only at that interval. So negative infinity, negative 3/4. But now it's concave up, this interval and this interval. And again, you may be tempted to write it as one interval, but technically when the second derivative is 0, neither concave up nor concave down. So we have to split that up at that point. So then it's concave up. From negative 3/4 to 0, union 0 to infinity. And that's the end of section 2.6.